Okay, everybody, how we all doing? Next lesson we're gonna do is talk about pH and the pH scale. And I think this is something you probably know a little bit about already, but we're gonna go through the theory of it. All right, pH scale, real quick. Um, One thing you have to remember about something about water is that you have in a sample of pure water, you're gonna have water molecules, and they're gonna be moving around. They're gonna end up hitting each other. You know, collisions are going to take place, and ever so often, a couple of times out of every billion, water molecules will slam into another water molecule. Okay, and one of them will transfer a proton or an H plus to another water molecule. So maybe if these two guys up here would hit, one of them would be transferred to the other. Okay, and then you'd get an H3O plus, right? And then you would get an OH minus. So one would lose one and one would gain one, and you'd have these two. All right. So if we look at that equation and we can say pure water can actually react with itself, we actually form two ions, an OH minus and an H plus. Okay. And these two are actually an acid and base. So really what you're making is you're making an acid and a base at the same time in equal amounts. Okay. And this is going to take place at equilibrium, which simply means that this will then revert back to, in reverse, two water molecules again. But again, this doesn't happen all that often. Like I said, it's probably about two times out of every billion that this will take place. So what we can do is we can write an equilibrium expression for this. And when we talk about this expression, what we're going to do is we're going to take the products, which are the two ions we're going to produce, the products here. And typically what we would do is we would take the products and we would put them over the reactants and make a fraction out of this. Okay, and then we would get something called a Kw. But in this case, what we're going to do is we're not going to write the reactants. And the reason we're not going to write the reactants is because these are pure liquids. And because they're pure liquids, their concentration won't change. All right, but if I gave you pure water and I asked you how much water there was in pure water, you would tell me 100%. So that's not going to change when it's pure. So we're not going to have any reactants in the expression. So the K means constant, the W means water. All right. And what we're going to find, and what we find by experiment, is that when we take the molarity, again, these are molarities, when we take the molarity of the acid and the molarity of the base in pure water, we're going to get this very small number, 1 times 10 to the minus 14. And that is by experiment. All right. All right. So this is going to be by experiment. So this has been a number that we've found, okay, by experiment. All right. So what we find here is that if you know that the H3O plus and the OH minus are in pure water together and they are equal, again, you're making one of one and one of the other. When you balance this, it's one of these and one of these, and they're equal. What molarity of each of these times by itself, really, because they're both the same number, would equal 1 times 10 to the minus 14. So if you think about that real quick, you're really just taking the square root of this number, because what number times itself would be this? So if you evaluate this knowing that they're equal, okay, you would get the fact that the molarity of the acid must be equal to 1 times 10 to the minus 7th, and the base must be equal to 1 times 10 to the 7th, so that when you multiply these together, you would add the exponents to 14. Okay, now again, this number has to stay true in any amount of water, any AQ solution. So anything aqueous, anything that has water in it, must be true all the time. So there's only one way that you can make 14 from two equal numbers, and that would be 7 and 7. So you might be able to see how we're developing the pH scale here. We're developing it from knowing this number here and then seeing where the acid base and this are the same. Now, we have a special word for that when the acid base are the same, and that simply means neutral. You've probably heard that before. So neutral is when acid bases are the same. All right, so I just here wrote out the scientific notation, but I wrote that out in numbers just so you can see what it looks like as a decimal. So if you take this and make it, so you can see that in pure water, and this is all pure water, that this number is extremely small for the acid and very small for the base. In fact, you probably could never taste this You wouldn't be able to taste the acid or the base here. You would just taste water, which doesn't taste like nothing. But at least you get the idea that the acid base is the same, and you can see how small this number actually is. So what does it really mean? Is that at pure water, there's very little acid and very little base, even though they're the same. Okay. Now this can never be zero, which means you can never have no acid or no base. You have this at neutral. All right. So a couple little things you want to do in summary here when we begin to develop this is that at 25 Celsius, the Kw, this number, is always equal to 1 times 10 to the minus 14th. Okay. And something really interesting that you have to know also is the fact that if you change the acid or the base, you change the other one. So if you change the amount of acid, then you change the amount of base. And I want you to think about it like a seesaw, where if you have two people on a seesaw, think about that. If you had a person sitting here and a person sitting here, and they were at level, so they were at a level elevation here, where one person was at the same level as the other, you would have equal amounts of both, right? So if the H is equal to the OH, there's only one way you could be equal. Now, if you were to change this, if the H plus should suddenly go up, then the OH would go down to compensate for this, and you would still be equal to negative 14. So we're going to get to this in a minute. All right. So for example, let's just say my H plus. Let's just say I put more acid in, and I increased the H plus to 1 times 10 to the minus 3. Well, if that was the case, then OH must change to get to 1 times 10 to the minus 11, such that the exponent of minus 3 and the exponent of minus 11 must equal that minus 14. Okay. Now again, if you think about it, if you look at this, you'll see that when you have 10 to the minus 3, you have much more acid than base, okay, if you're at 1 times 10 to the minus 11. So if you were looking at your seesaw, right, well, it wouldn't be like that. It would be like this. Your seesaw, you would have much higher acid and much lower base if they were on a seesaw together. And that's the way it would look. All right. So what we're going to do is come up with an expression so that we can somehow make this a little bit easier to deal with, because dealing with molarities and all these zeros and numbers and minus exponents and things like that make it very tough to have casual conversations about acids and bases. So what we do is we develop the pH scale, and what we're going to simply do is take the acid concentration, the H plus concentration. We're going to use this. Okay. Now this could also be H3O plus. Remember, we have two words for the same thing. And what we're going to do is we're going to find the negative log of this. So if you were to take your calculator out and hit the negative button and then the log button, okay, and then you'll open up the parentheses if you have one of the TI-83 or whatever calculators, all right, and then you take this number and you put 1 times 10 to the minus 3 in here. Now I know the times 10 can be the EE button, and that's above the comma. So if you hit second function EE, you'll get the times 10. If you evaluate this in your calculator, you will actually get a big 3. So what the calculator does when you take the negative log function is it simply pulls out this number, makes it negative, so you'll be the negative of the negative, and turns it into a whole number. Because a log is really an exponent of a number. And that's what the pH is. Okay? So what we do is we define the pH as the negative log of whatever the concentration is in molarity of the acid. Again, it will be the acid of this. Okay? So if I do that, if I take the negative log of 1 times 10 to the minus 3, I will get pH 3. All right? And that's exactly what the pH is. So we don't have to walk around saying, the acid molarity is 1 times 10 to the minus 3 moles per liter. We could just say pH 3, and people know what you're talking about. All right, so that's very nice to use in a lab, very nice to use conversationally, very nice to use for communication. So it's actually a clever little thing and a clever use of logs. So even if you really don't like logs, which is a lot of you, this is actually pretty cool. All right, so how do we use this? How does this make life a little bit easier for us? Okay, we take a look at this nice little chart here, which helps us look at the relationship between acid, which is your H plus, base, which is your OH minus. Okay, and you'll see your acid is here, your base is here, And let's just start with the neutral point. You'll see the neutral point is where acid bases are equal. Okay, and since we're taking the negative log of this, okay, you'll see that's what the pH is. The negative log is the pH. You'll see that anytime you see the negative number here, the negative of that negative number is the number that you see in the pH scale. Okay, a couple things to keep in mind. Notice that when you get more acidic going this way, that number will change, but then notice that the base changes to keep it at 14. Okay, so whenever you have the acid and the base, when you add those exponents, you'll always get that negative 14 that we were talking about. So in 5 and 9, and 4 and 10, and 3 and 11, and 12 and 2, and 1 and 13, and so on. Okay, so as you go up, notice that this number actually gets bigger. So you increase your acidity because you're adding more acid and less base. So this is more H plus, okay, and less OH minus. So I'm just putting these to remind you. All right, and the reverse happens here. You get less H plus and more OH minus. Okay, and that's what you see when you see here. All right, so a couple of things along the way you want to be aware of. Number one, there's three possibilities, right? And the three possibilities, okay, are a neutral solution where you could think of your, go back to my yellow pen. That's not working. Okay. Well, three solutions. So you have a neutral solution, which is the acid equal to the base. You can have an acidic solution, where you have the acid is greater than the base, or you can have a basic solution where you have the base is greater than the acid. You can have that way about it too. All right. And when you go to, so a couple things also you want to realize is that each pH point, when you go from, like, say, pH 2 to pH 3, that's going on an exponent from 2 to 3. So that's going to be a 10 times difference. All right. So each pH point is actually be a 10 times difference. So if you went from 2 to 3, that would be 10 times less acid. If you went from 2 to 4, however, right, that would be 100 times less acid. If we went from 2 to 5, that would be 1,000 times less acid. So each time you move a full pH point, you're moving that amount. That's going to be the acid change, right, by about 10. All right, so that's what I'm trying to tell you here in this one is 10 to the third. Okay, 10 to the third. If you go to 10 to the second, that's going to be that many times more acid than you would be doing. Okay, the exponents here of H and OH must add to 14 in this case. So that's going to be really important. All right, unfortunately, I'm having a problem with my color thing here. So what I'm going to try to do is we'll deal with that later, and we'll just deal in black. So I hope you can see it. But all right, so if you have a pH 5 here, okay, my acid concentration is going to be 1 times 10 to the minus 5. I'm hoping you can see this, but we'll try to do the best we can. Is 1 times 10 to the minus 5. Okay, if I have my OH, then if I'm a minus 5 here, then to make 14, my base would have to be 1 times 10 to the minus 11. All right, a lot less base, so less base, more acid. If I have an acid concentration of 1 times 10 to the minus 3, then my pH is going to be 3. All right, and my OH concentration is going to be 1 times 10 to the minus 11. Oh, made a little mistake. This should be a 9 here. Sorry, guys. So 1 to 10 to the minus 9 if you're watching this. Okay, it's a pretty ugly 9, but we'll keep it. All right. Now, if you had a base that was 1 times 10 to the minus 4, then of course your acid would be 1 times 10 to the minus 10. And remember, the pH always goes with the H, so then I would have a 10 as my pH. Right? So we could see it in that way, like that. So that really helps us to see it. All right. And moving on, we can then play around with going back to yellow a little bit, and let's practice our pH stuff. So let's just say we had a pH of, let's go back. Okay, so let's say we had a pH of, we want to know what is the pH of a solution that has a hydroxide ion concentration of 0.001. And let's change that quickly to 1 times 10 to the minus 4. You may want to do that. Now, watch the trick on this, because hydroxide is what? That's actually a base. And we want to know what the pH is. So we have to know what the acid is. This is the base concentration, because the base is OH. That's the hydroxide ion. So we know that the hydroxide ion is 1 times 10 to the minus 4. Then the H plus must be 1 times 10 to the minus 10. And since the pH is related to the H plus concentration, my pH must be equal to 10. That's going to be important. Okay, so we got the idea behind that. All right. So how about another little thing we can do? Given a solution with a hydrogen ion concentration, and that's H plus of a concentration of that, okay, find the pH. Well, since we're talking about the acid, that's the H plus, that's going to be a pH of 8. My OH concentration would have to be complementary to this, whatever makes 14. So that would be 1 times 10 to the minus 6 moles per liter. All right. My litmus color, if you remember back, my litmus color would be red. Okay, you can get that from table M, which we'll do in a minute. Phenolphthalein, because it's a basic solution, I'm sorry, this would be blue. Blue in a base, it's basic solution. Okay. Again, you'll see that in table M. Phenolphthalein in a pH 8 solution would be pink. Okay. Number of times less acidic from 5. So think about that. So you go 5, 6, 7 to 8. You would go 1 pH point, 2 pH point, 3 pH point. So that's really 10 to the 3, which is 1,000 times different, right? So given a solution pH 2, find the H plus concentration. If it's H plus and that matches my acid, I would be 1 times 10 to the minus 2 moles per liter. My OH would be complementary to 14, so that would be 1 times 10 to the minus 12 moles per liter. I would be, pH 2 would be acidic solution, okay? And my litmus color would be red in an acid, and my phenolphthalein would be colorless in the acid. So again, both of these are table M in the New York State reference table. Good? All right, so that takes care of pH. That's a good little practice for that. Very simple kind of thing on that. Okay, number of times more acidic than pH 4. Again, you would be 100 times more acidic, because you would be going from a pH 4 to 2, which is 4 to 3 to 2, which is times 10 times 10, which is 100 times. So just be careful on these type of questions. They tend to show up on the exam. All right. The last one here is something called indicators. And indicators are ways to indicate whether you have an acid or a base. All right. So a couple things. They use to indicate acid or bases. There are colors that are pigments that we get from plants, okay, and other substances. Okay, they change color during pH changes, and the key is they change color during the pH changes. That's important to know. Okay, all right, and that's when they're most useful. When you go through the range of their change, you're going to blend the colors, and this is a little bit issue with this, so we'll get this in a minute. Okay, for example, if you take a look at methyl orange, I want you to focus in on methyl orange for a minute down here. All right, if we look at this, all right, we'll see methyl orange has a range of 3.1 to 4.4 here. Okay, 3.1 to 4.4. And simply what that means is that before 3.1, okay, if you look at this beforehand, okay, and you look at this, if you look at this before 3.1, you're going to take the first color. So from all the way up to 3.1, methyl orange is going to be red, okay? During the change from 3.1 to 4.4, and you're going to change from red to yellow, which is actually orange. Hence the word methyl orange. After 4.4, you're going to be yellow. All right? So again, that's important to know because methyl orange is only really useful when it changes color through that pH range. Now, if you take a look at methyl orange, you'll see it over here in our little chart here. And what we're going to find is that you can see basically its range from basically pH 0, which is here, all the way through about 3.1, where it says it's red. It's red this whole way. Okay. And over here, it's yellow. This whole range is yellow. This whole range. Okay. It's only active in this range of pH change, which is where it becomes this red to orange. So the idea behind using an indicator is you really want to use an indicator where you have those color changes. Okay, bromothiamyl blue and litmus are very useful because right around pH 7, the neutral range, is where they're useful. So a lot of times in food science or in agriculture or growing plants or in body chemistry, because we typically live around the neutral range, these are very common indicators. So litmus is common, bromothiamyl blue is common. Again, even phenolphthalein around the neutral range in here, you're changing from color to pink, is a very useful indicator. All right, it doesn't make sense. Let's just say, I mean, for example, if you're working with, let's just say you're working with something, down with litmus, but your work is working between 1 and 4. Let's just say you're in a lab and you're working on a project, and that project is something that changes pH between 1 and 4. Like if you use litmus, you're not going to know whether you're pH 1 or 4 because the litmus paper doesn't change. So what's the point, right? The point of using litmus as an indicator is silly because it's going to be red at pH 1 and it's going to be red at pH 4. If you were working with litmus and you were changing pH from 6 to 8, litmus is going to be a good choice. Okay. Last but not least on indicators, you just want to remember what your colors are. I know sometimes we forget. Okay, yellow to blue is going to give you a bit of like a green color. So that's going to be green. Colorless to pink is easy. That's just light pink. Red to blue is going to be a purple. Okay. Yellow to blue is going to give you a green. Okay, and again another green. So yellow to blue, and your yellow to blue, and your yellow to blue is going to give you like this green color. Okay, and red to blue will give you the purple color, and again red to yellow will give you an orange. So that really covers indicators. Just make sure you read these things carefully because on the Regents exam or in any other test you're taking, it is kind of easy. You just have to be careful that you know that the first number in this chart is what it is up to that color, and then after it becomes that color the whole way through. All right. So that is what we're talking about. That ends this lesson. Have a great day.